In this video, we will introduce t-distribution and show how to calculate t-distribution and t-test in Python. The t-distribution is related to normal distribution and chi-square distribution. So we look at a variable called t. If this variable is a two-part division and the numerator is a standard normal distribution variable and the denominator is the square root of a chi-square distributed random variable divided by its degrees of freedom, then we can say t is a t-distributed random variable with degrees of freedom nu. And this degrees of freedom number is same as the degrees of freedom of the chi-square distribution in the denominator. And the t-distribution has the density form here is a factor times 1 plus t squared divided by the degrees of freedom, then have a negative power with half of the degrees of freedom plus 1. Then the factor is a gamma function's division. So the numerator and denominator both are gamma function. And the t-distributions variable available from negative infinity to positive infinity. T-distribution is quite often used in the test of population mean. So if x1, x2, and xn be independent random variables from normal distribution with mu, mean, and standard deviation sigma. So if we let x bar equals the sample mean and s square is the sample variance, just note sample variance is the sum of the square of the difference between value and x bar sample mean divided by n minus 1. So we divided by n minus 1 here because 1 degrees of freedom is lost when calculating the x bar. So if we have calculated x bar and s square, then the t value, we can call this test statistic from the sample equals x bar minus hypothesis population mean value, then divided by sample standard error divided by the square root of n at sample size. Then this t-test statistic has a t-distribution with n minus 1 degrees of freedom. So in this figure, there are 3 t-distribution density curve. So this is for t-distribution with degrees of freedom equals 2. And the middle one is degrees of freedom 5, and highest one with very large degrees of freedom. So the highest one is also called normal distribution curve, because if the degrees of freedom in a t-distribution becomes very, very large, so it is very close approximate to a normal distribution. So usually t-distribution's density curve has flat shape than normal curve and has a long tail than normal curve. Now this table is called the t-distribution critical values table. So this, for example, is the t alpha here. So we usually use t alpha as the critical value for test of mean, population mean. So if the calculated sample test statistic larger than this value or less than the negative of this value, the other side, so we can say the test is significant. This is equivalent to that we can get a less p-value than alpha here. So in Python, we use the module scipy.stats import t module. Then from the t module, there are 4 functions called pdf for the probability density, cdf for the cumulative probabilities, and ppf for the quantiles, and rvs for the random number generation. So here df parameter means degrees of freedom, and loc is for the location parameter. Here default is 0. Default is 0 here. So next we will show how to use t-distribution in Python. So first we import scipy.stats t module and numpy module and matplotlib. So the first function called pdf with a quantile, degrees of freedom, and location. So we set a quantile value between -8 to 8 and with the gap 0.1. And we set the degrees of freedom 10 and the location here too. Then we can use t.pdf to calculate the density value with the corresponding quantile value. Quantile here means t-distribution is a random variable. So this variable means this variable has t-distribution, but we have to calculate the density here. We set a df equals df10, but we use default location here now. Calculated, then we can plot the relationship between quantile random variable and the corresponding density. So this is a quite symmetric t-distribution density curve from the value between -8 and 8. You can see the most of the probability stay within -4 to 4, right? Because the density from -8 to -4 is 0, almost 0. So here, the area between -4 and 4, almost 1. So next we can calculate again for this random variable's density if we set a location equals 2 here. So we plot again. So because we set a location is 2, so we know that t-distribution is symmetric. So the location here is also the mean value. So you can see the in this example, most of the value is also symmetric because we did not choose -16, right? Because the location is 2. So here -4 equals, for example, -2's density is same as 6 here, right? So next, the function called cdf is used to calculate the cumulative probability for the corresponding quantile value. We also set the quantile and df and the location same as before. Then we can use the CDF function to calculate the cumulative probability for each of the quantile value. Next, we can plot the relationship. It's quite clear. So because the density between this range almost zero, so the cumulative probability does not increase. Then have start to increase, and to this value does not increase because the density becomes zero again. Yeah. And next function is called PPF. Is to calculate the quantiles value from a given cumulative probabilities. And PPF is actually the inverse operation of the CDF, right? Where PPF calculates the quantile values from the given cumulative probabilities. So we set DF and location same as before. We also create probabilities array between 0.01 to 1, because probability cannot be larger than 1, and with the gap 0.01. So we can calculate quantile value or the random number value from t-distribution if we know the cumulative probabilities. And next, we show the relationship between the probabilities, cumulative probabilities, and the quantile value. This curve is the inverse curve from the PPF, from the CDF, cumulative probability. So for example, 0.6 here, almost, we can see 0.5, for example, here, about 2, because this t-distribution has a mean value, we set the location 2 here, so which means 50% of the value in this distribution has 50% of the random variables has value lower than 2, right? So the last function is called RVS to generate random numbers from t-distribution. So we can create, for example, 10,000 random numbers from t-distribution with 10 degrees of freedom. So we use t.rvs 10, size is 10,000. Then we can plot this created value in a histogram with bins 50. So this curve is very similar as the density curve, but this is a histogram. The shape is quite same. It's almost symmetrical, but not exactly symmetrical because this is a random number generated, so it's not perfect symmetric. For example, here, not exactly the same symmetric, right? Because we set the location default value, so you can see the highest frequency value is 0. Mean value, also median value, also the mode in this distribution is 0. So next we can set the location to 5, then create also 10,000 values. So plot again histogram. So this time the mean value or the mode is very close to 5 now, right? So now we will show an example of using t-distribution to do t-test for the population mean. So the example is a chemical engineer claims that the population mean yield of a certain batch process is 500 grams per milliliter of raw material. So to check this claim, he samples 25 batches each month. So if computed t-value falls between minus t0.05 and t0.05, he is satisfied with this claim. What conclusion should be drawn from a sample that has a mean x bar equals 518 grams per milliliter and a sample standard deviation s equals 40 grams? Assume that the distribution of yields to be approximately normal. So this is a typical t-test problem, right? Because the population is normal and we use the sample mean and a sample standard error to do the test. So the test statistic calculated in this form will have a t-distribution, right? So we import module called mass because we use for the square root. So first of all, we have to calculate the critical value of the t-distribution with 24 degrees of freedom and 0.05 here. So we want to calculate the critical value t alpha here because in this test use 0.05 or alpha is 0.05. So we have to calculate the t alpha. Do not use the table, just use our program. So the t critical value equals the t dot ppf. ppf means quantile. We want to calculate the quantile from the given probability. So the given probability is 1 minus 0.05. Because the ppf is calculated the cumulative probability to the t alpha. So this is white area. The white area under the curve is 1 minus alpha, right? So we use t.ppf 1 minus 0.05, then use 24 degrees of freedom because there are 25 observations in sample. So it is about 1.71 for this t value, for the critical value in this curve, right? So next we calculate the t sample. So sample statistic, test statistic. So t sample statistic is from this form, right? We have mu, assume the mu, and we have standard error from the sample. We have the x bar for the mean, for the sample mean value, right? And n for the sample size. So everything is ready to calculate the t sample. Just fill in the form. Then t sample is 2.25. So we can do another step from this t sample. So this is sample test statistic. We can also get the p value. So t sample is here. This is the t critical value for the test critical value. T sample, because 2.25 is almost here. So we can calculate the probability, change the probability associated with this test statistic here, right? So we can use the CDF function now. t.cdf, t sample, then use 1 minus, calculate the probability, we get this p value. So it's about 0.0169. So the conclusion can be drawn because t sample test statistic from the sample larger than t critical value, because 2.25 larger than 1.71. Also means p-value calculate less than 0.05. So 0.05 is the significance level we assumed before we test, right? So the engineer is likely to conclude that the process produced a better product than he thought. So which means these samples comes from a population with a larger than 500, not 500. So because if we assume the population mean the 500 is correct, then there's only about 0.01 probability can get such sample. So this is quite a low probability. So we can safely reject the hypothesis that the population has a mean of 500, right? So I'll say in this test, the test result is significant. It's significant because the test statistic larger than the critical value, and also the p-value, this is same as the p-value calculated from the sample is less than the p-value, the significance level 0.05. So the hypothesis of population mean is 500 is rejected. Thanks for watching.